morning, ladies and gentlemen. Let me start my talk. First of all, before I will talk about our experimental efforts of microfluidics, I would like to introduce Czech Chemical Society. I would like to thank organizer for inviting me also. So it's an outline of my talk. So first I would like to introduce Czech Chemical Society, which was established in the 90s after the Second World War in former Czechoslovakia, and it connects chemical engineers through industry and academics also. And here you can see the current president of Czech Chemical Society is Jiří Drahoš. The society is a member of European Chemical Engineering Societies, and this organization is organized international congresses HISA. You see here, these congresses take place in Prague every 2 years, and these are one of the most famous congresses of chemical engineering over the world. The last congress was this year, but in 2024 will be next congress, and I would like to invite you to visit Prague. It's a beautiful city, and I think the conference is also very nice, and you can find very interesting topics there. So let's go back to my talk. First, the motivation of the work. We are playing with microfluidics, microreactors, and microseparators, and we combine them and trying to find a way how to efficiently produce special chemicals and also pharmaceuticals. Of course, if we work with microfluidics, it's simple to prototype these processes, so we don't need weeks or years for development such as process, but we need days or weeks. We also try to do all processes continuously. No batch processes are carried out in our systems, but we work really continuously, which should provide reproducible results and a reproducible product. And one most specific feature of our work is to use electric field for separation, and we can use this electric field in microfluidics because there is a high surface to volume area, and we can easily remove released heat during the during the flow of electric current. I would like to show you 3 case studies we dealt with. First one is the continuous enzymatic synthesis of cephalexin. The cephalexin is one of the most important antibiotics currently used, and the synthesis, enzyme synthesis, is interesting way because we start with two substrates, phenylglycine methyl ester mostly as an acyl donor. It reacts with enzyme penicillin acylase, and the enzyme phenylglycine complex is formed, and this complex then reacts with cephalosporanic acid and forms cephalexin, which is the final product. But this reaction is an equilibrium reaction, so it can be again this complex, or the product can be decomposed by the same enzyme back to cephalosporanic acid, and the enzyme phenylglycine can be hydrolyzed by side reaction to free phenylglycine, which is not utilized in the reaction, so it's a side product. So if you do in batch, you see that we start with some concentration of both substrates, phenylglycine methyl ester and the cephalosporanic acid, and cephalexin is formed. But at some time, at some residence time, about 30 minutes, maximum is achieved, and then the reverse reaction becomes dominant, and cephalexin is decomposed, and you see that phenylglycine methyl ester is exhausted after some time. So it's necessary to carry out the system under controlled regime with a proper residence time. Another task is how to separate cephalexin from the reaction mixture. We use here free enzyme penicillin acylase, and all chemical components are dissolved in water, of course, or in buffer. So we decide to combine the reaction itself with in situ separation or in situ extraction of the product using aqueous two-phase systems. You see here aqueous two-phase system, how it works. We have two aqueous phases. They are immiscible, and if you look in detail at the color, you see that the extraction occurs here when the color chemical enters the second phase during the process in this membrane channel. We produce an optimized composition of aqueous two phases. In fact, the composition is from three different components. One is the is a polyethylene glycol with this molecular weight, phosphate salts, and water. And this mixture splits into two phases: light phase, polyethylene glycol phase, and the salt phase. And what is important here, that protein penicillin acylase enzyme is accumulated in the salt phase, but the product cephalexin prefers polyethylene glycol phase. So we can use this system directly in our system. There is a scheme of the system, and you see that it's nothing very difficult, or you see that we have a T connector where slug flow is formed, and here we introduce enzyme in the salt phase, and here reaction substrate in the polyethylene glycol phase. And here what happened, substrate is transferred from one phase to the other phase, where it is converted to cephalexin, the final product, and the cephalexin is transferred back to the original phase. From the original, there is a settler, gravity settler, which is quite simple device, and cephalexin is collected here in this reservoir. but the enzyme, because it's soluble and is quite costly, is recycled back to the system here. But the problem is that side product phenylglycine accumulates in the system, and especially in the heavy salt phase. So we had to develop a microdialysis unit which employs tubular membrane, and we continuously dialyze the product and purify the enzyme again, so the enzyme could be returned back to the reactor here. So as you can see, we operated the system continuously about 5 hours, and here you see on this picture composition of the product. You see that this is the red line is a cephalexin concentration. It's a slightly decreasing concentration at the output, but still is quite high related to reaction conditions, and no clogging observed in the system. So it was one case study I would like to show, and this is another one. It's a continuous synthesis of 6-aminopenicillinic acid, again by penicillin acylase, and this system or this reaction serves for the production of this product, 6-aminopenicillinic acid or 6-APA, and this is again a source or a precursor of beta-lactam antibiotics. It's not a big challenge to synthesize 6-APA because the substrate is converted by penicillin acylase within a few minutes, at least almost at the 100% conversion. But the problem is now, if we use a soluble enzyme and we have also the products in soluble form, we have to separate them because the enzyme is costly, and we must reuse it to provide high utilization. So I think the biggest challenge here was to separate the enzyme and the reaction product. For this, we again produce this system. It consisted of several syringe pumps. One pump introduced enzyme, the other pump penicillin G, which is a substrate. Here we have a capillary microreactor immersed in a bath, and then a reaction product containing enzyme and 6-APA is introduced in membrane module. Because 6-APA is negatively charged under reaction condition, it can be separated through the membrane by orthogonally applied electric field, and you see that the product can be collected here in this reservoir. The other stream contains enzyme, and it is led back to the dosing unit here, and it's again highly utilized in the system, which operates continuously. Here is a detail of the membrane separator. The point here, the central part is a dialysis membrane with a properly chosen molecular weight cutoff. This provides separation of enzyme, which has a molecular weight at about 70,000 Daltons, and low molecular 6-APA. The low molecular product easily permeates through the membrane. Here you see, I think these are permeate and retentate sides of the membrane unit. And what is important is to connect these systems with the source of electric current, but you cannot do it directly by immersing electrodes inside, because then you miss some reaction products, and also the product will be contaminated by a side reaction at the electrode. So this separation we did by means of cation exchange membranes, which are electrically conductive, but they don't allow to permeate the negatively charged ions. So our product is negatively charged, so it cannot escape from the system. And you see that here you see the composition of the reaction products after 6 hours operation. Yeah, maybe it's a slightly decreasing trend here, but still the system operates for a long time. And the final study I want to show you is a study focused on synthesis of mandelic acid enantiomers that we carried out in a similar system. So we start the synthesis with a substrate. Substrate is methyl mandalate, which has 2 optical forms, and it is decomposed by enzyme lipase. Either R mandelic acid or S mandelic acid is formed in this reaction, and what we can find in literature, each lipase prefers one of the enantiomers to be produced. There is no 100% selectivity, so you can produce a particular enantiomer with a certain enantiomeric excess, and the lipase we used here in this case prefers formation of R mandelic acid. And the point here is that the substrate is not, so if we convert racemic substrate, this mixture, with 100% conversion, you will obtain again a racemic mixture of mandelic acid, which is not our aim. Our aim is to form mandelic acid with high enantiomeric excess of one enantiomer. So the conversion is only partial, and now the problem is how to separate mandalate and mandelic acid, and the separation is like easy because mandalate is not charged molecules, it's electroneutral molecule, but mandelic acid releases in a neutral pH this proton, so it's again negatively charged, and we can use again simply the similar separation unit for separation of the product. So here is a scheme of the system. We use a picket bed reactor with immobilized enzyme now, and the reaction products, and together with unreacted methyl mandalate is led to separation unit, where orthogonal electric field is applied, and the mandelic acid permeates through the membrane to acceptor stream, and because not charged, methyl mandalate remains in the retentate and can be used later again. Here is a detail of the system, packet bed reactor that we constructed, and again a membrane system here. So it was nice that the first talk in this session how to produce a high amount of valuable product. Here our performance in our microfluidic system is 1 gram of mandelic acid enantiomer per day, which is not very high productivity, but it can be easily numbered up or scale up by increase the surface of the separation membrane. And what is important that we can operate it continuously for a very long time, because packet bed lipase, immobilized lipase in peptide bed reactors is quite stable, and we achieved the enantiomeric excess of almost 60%. And if we impose proper electric current through the membrane, you see that we can separate almost 100% of synthesized mandelic acid from the unreacted methyl mandalate, which is, I think, quite good result. So let me conclude our result with, we constructed a 3-modular microfluidic system for synthesis antibiotics, precursor of antibiotics, and optical enantiomers. All systems operate continuously, and we were able to utilize either aqueous two-phase system or orthogonally applied electric field to provide highly efficient separation of the reaction product. Finally, I would like to thank to my colleagues. We are a very small microfluidic group, and finally, I would like to thank you for your attention.
Thank you, Professor Michal. Any questions from the audience? No? I have one. When you separate your mandelic acid enantiomers, did you see any aging effect because you have to apply electrical field? For example, leading to some lower separation efficiency?
No, in fact, there was no aging effect. It can be observed probably on membranes, but we operated through several weeks, and parameters of the system remains almost constant. But of course, sometimes it will be necessary to exchange cation exchange membranes because they can be some dust appears, and of course the aging of the internal structure is also possible. So after let's say several weeks it can be exchanged, but these membranes are cheap, so it's not a very big problem.
Any other questions? If not, let's thank Professor Michal again.